Dear students, let's continue our practice on Mathematical Analysis 1. And let's continue the previous topic, numerical sequences. And now we'll consider some examples on limit of numerical sequences. Let's consider the first example. Example number 1. Here, calculate the limit. N tends to infinity 1 over 1 times 3 plus 1 over 3 times 5 plus etc. plus 1 over 2n minus 1 and 2n plus 1. So, let's calculate this limit. What should we do? Firstly, to calculate this limit. Firstly, we need to compute this sum. Here we cannot directly calculate this for each terms, and that's why we will firstly find the sum of this sequence. So, how to find? Let's remember. So, if we have the expression 1 over n times m, we can continue it like 1 over m minus n times 1 over n minus 1 over m. So we will use this formula for this sequence because we have instead of n, m, n, we have respectively 1 and 3 or 3 or 5. So in generally 2n minus 1 and 2n plus 1. So let's continue now our example. Here what we get, limit n tends to infinity. So let's use this formula. It means 1 over 3 minus 1 times 1 over 1 minus 1 over 3. We consider this example in mathematical induction also. When we prove this statement, we consider this one. So 1 minus 1 over 3. Next one, plus 1 over, similarly, 5 minus 3, and 1 over 3 minus 1 over 5, so on. So the last ones are 1 over 2n minus 1 minus 2n plus 1 minus 2n minus 1 here, and in the bracket we have 1 over 2n minus 1 and minus 1 over 2n plus 1. So, and now we have the following one now. So, what we get? We get here, difference is 2. 2, here also 2. Yeah, so now we can factorize this expression. And what we get if we factorize it? So, if we factorize it, so we have 1 over 2, limit n tends to infinity, 1 over 2, then here we have 1 minus 1 over 3. Next one is 1 over 3 minus 1 over 5. And the next one would be, for example, plus 1 over 5 minus 1 over 7, etc. So, and plus the last ones are 1 over 2n minus 1 and minus 1 over 2n plus 1. So now we have the next one, limit n tends to infinity. So they are cancelled. Look here, minus 1 over 3 plus 1 over 3 minus 1 over 5 plus 1 over 5, and this one is the next one, and we can continue this progress till this one. So we have the first one and the last one just. So now the next one is 1 over 2 in the bracket 1 minus 1 over 2n plus 1. So we can compute it now. And when we complete it, we have limit n tends to infinity. So give a common denominator here, 2n minus plus 1. So then we have 1 over 2 times 2n plus 1 minus 1. So it means 2n over 2n plus 1. So the limit of this sequence is now, here we have the same powers n and n. So it means we should take as limit of this term of this sequence is like 2n over 2n, the ratio of coefficients, main coefficients. So here we have just 1, and 1 times 1 over 2, it is half. So the answer is 1 over 2. This is our answer. 1 over 2. Okay, so now let's consider the next example. The next one now. The second one is limit n tends to infinity 2 plus 3n over n squared plus 5 sine n. So let's consider this sequence and the limit of this sequence. Here, how can we calculate this limit? So to calculate this limit, firstly, we need to consider this part. So 2 plus 3 n over n squared plus 5. What can we do here? So it is, however, we have in n first power and in denominator we have the second power. It means that the power of denominator is greater than power of numerator. So it means it goes to 0 because it goes to infinity faster than this one. And next thing, here we have sine n. So sine n is bounded function. Sine x is bounded function. The domain is the range of sine n. It is from -1 to 1. Here, that's why we can use the n tends to plus infinity. It tends to 1 because the greatest value of sine n, it is 1 when n tends to plus infinity. So now what we have, this is 1, this is 0. So the answer is 0 times 1, it is 0. This goes to 0, it goes to 1, and the answer is 0. This is our answer. And now, let's consider the next example now. Example number 3. Limit n tends to infinity 3 this one 1 squared plus 2 squared plus 3 squared, etc. plus n squared and over n cubed. So here how can we find the limit of this sequence? In this case, again, we need to calculate the sum of numerator. And when we talked about mathematical induction, we used this one. And we proved this statement. And what was the sum of square root of numbers? 1 squared plus 2 squared plus 3 squared plus etc. Let's remember one more time. N squared, it is n plus 1, 2n plus 1 over 6. So now we will use this one, and we will put this instead of numerator. And when we put it to numerator, we get limit n tends to infinity. Here we have n cubed, but in the numerator we have 6, so it will be 6n cubed, and in the numerator n plus 1, 2n plus 1. So, and now we can calculate this limit. How? Let's consider n powers of n. So here, first power, and first power. When we multiply them, so n times n, it is n squared, times 2n, it means 2n cubed. Yeah, we need to open or use just the ratio of powers of main coefficients. Ratio of coefficients of powers. Here, if you open, it gets n squared plus n, 2n plus 1. Of course, here we have limit, n tends to infinity, and in the numerator we have 6n cubed. So here we have, when we open the brackets, 2n cubed plus n squared. We need just greatest power. The other ones we don't need, because here we have n cubed, and here also the greatest power is n cubed. So let's write the other ones also. So 2n squared, here 2n squared, and plus n over 6n cubed. Now, when we divide by greatest term, here it is n cubed, we get the ratio of the coefficients 2 over 6. As here we have, if we divide by n cubed, it is 2 plus 3 over n, we can add them, plus 1 over n squared over 6. We divide by n cubed, numerator and denominator. So now they goes to 0, and we get just 2 over 6 or 1 over 3. This is limit of our sequence. Let's consider the next example. So number 4. Let's find a limit. Limit n tends to infinity, cubic root of n plus 1 minus cubic root of n minus 1. So find this limit. To find this limit, firstly, we need to remember the formula a cube minus b cube, because here we have cubic roots. And when we use this, if we use this formula, we can get the limit which can we calculate. But in this case directly we cannot calculate, because if we put here n tends to infinity and tends to infinity, it goes to infinity and infinity, the minus infinity minus infinity, it's unknown, so it's impossible. So that's why we cannot do it directly. And let's use this formula, a cube minus b cube. So to use this formula we need to calculate, compute the next. We have a cube minus, if we write a cube minus b cube, we have a minus b, a squared plus ab plus b squared. Yeah, so short multiplication formula. Then if we use this formula, we need to multiply these brackets to here and divide by these brackets. And so it is limit n tends to infinity, cubic root of n plus 1 minus cubic root of n minus 1, and let multiply to this, to the next bracket of this formula. So it will be cubic root of n plus 1 squared plus cubic root of n plus 1 n minus 1, and the last one is plus the cubic root of n minus 1 squared. So, and our this one, this bracket, let's write one more time. So now, let's continue. Here we have the formula in numerator, and we can write by this formula a cube minus b cube. So this one is cubed minus this is cubed. The second one is cubed. So, and if we take the power cube, they are cancelled, the power root and power. So we have just n plus 1 minus n minus 1, but however we have minus in the middle, we have n plus 1 one more time. So they are cancelled, and in the numerator we have these brackets. And now, so limit n tends to infinity. In the numerator we have 2, and in the numerator we have, let's consider now the denominator. So here we have what we get, n squared, and n squared. We have pluses here, yeah. So, and when n goes to infinity, it goes to infinity, because we add these expressions, the first, second, and third expressions. That's why they goes to infinity. And we'll not write again one more time these brackets, but it goes to infinity. So now in the numerator we have just number 2. So when the numerator goes to infinity and numerator we have 2, the answer is 2 over infinity or 1 over infinity. It is 0. So the answer of this limit is 0. This is answer. Okay. Next one. Let's calculate this next limit. Limit n tends to infinity. This is number 6, I think. So n plus 2, n plus 1 minus square root of. square root of n minus 1. So let's calculate this limit. To calculate this limit, again, we will use the formula, short multiplication formula. Here we need to use a squared minus b squared. Let's remember the formula. It is a minus b and a plus b. Because we cannot calculate this limit directly. Again, here we have infinity, here we have infinity. Infinity minus infinity, this is unknown. So in this case, if we multiply to conjugation of this expression and divide by it, we have the formula and we can compute the next limit. So let's continue. Limit n tends to infinity. So write this expression. So, and multiply to conjugation with plus. And plus 2 and plus 1. I think it's clear, yeah. And in the middle we have just plus. This is conjugation form. n minus 1. So, over and divide by this one, this expression, n plus 2, n plus 1, plus n plus 1. We didn't change our example, but we use it. For using this formula, we changed form of this example. Now, here, multiplied and divided. So, this numerator now gives us the formula a squared minus b squared, because a minus b, a plus b now. So, and the answer is n squared. This one is squared, so they are cancelled. The square root and the square. So, n plus 2. N plus 1, so minus n minus 1 over, let again one more time, let denote by square brackets is over this square bracket. Now, here we have, if we open these brackets, we get limit and tends to infinity, n squared plus n plus 2n plus 2. And here we have minus n squared and plus n over the square brackets. So, let's consider the numerator firstly. N squared and n squared, we can cancel them. And we have n plus 2n and minus n. Plus n, again, one more n. So here we have 4n. So, let's continue this one now. Limit n tends to infinity. Here we have just n plus 2n, 3n plus n, it is 4n. 4n plus 2. And over. And now, let's consider one more time the denominator here. Yeah? The denominator is this one, square brackets, I mean. This is, here, if you open these brackets, what we get? We get square root of n squared. This one, yeah, n squared plus n plus 2n plus 2, or n squared plus 3n plus 2. And when we open the next one, it is plus n squared plus n. So now let's consider the denominator. So in the denominator we have here n squared, this is greatest power, and n squared, this is also greatest power. But our n squared is inside of the square root. So it means we have just like this expression, square root of n squared. What is it? When if n is natural number, this is just n. This is just n. So it means we have the greatest power is, it's not n squared here. The greatest power is situated inside of the square roots. So now we have here n and n, the greatest powers, and we have coefficients, just 1 and 1. So we can take again the ratio of coefficients of the greatest powers, terms with greatest powers. So in this case we have n and the coefficient is 4. So here we have 1 and 1. If we take square root from 1, it is 1 again. And we can add them. Now 1 plus 1, we have 2. Or we can write like, if we divide by n, so this is, if we divide by n, we have limit n 4 plus 2 over n, and here we have, if you divide by n, in the square root it is n squared now. So now we have 1 here plus 3 over n plus 2 over n squared, and the plus here 1 plus 1 over n, and now there goes to 0, and we have just 1 and plus 1, 2, and it goes to 0 again. So now they go to 0, and this one's, now the answer is limit n tends to infinity, or we can write just directly. Here we have just, we don't have anything out without 4 and 1 plus 1, 2. So the answer is just 4 over 2, or just 2. This is our answer. The limit is equals to 2. Okay, let's continue. So the next example is here, limit n tends to infinity, of course. So n squared plus 1 over 2n plus 1 minus 3n squared plus 1 over 6n plus 1. So in this example, can we calculate the limit directly? No, because if n goes to infinity, it goes to infinity, it goes to infinity, we have infinity minus infinity. Just infinity minus infinity we have. And this is a known expression. So that's why we cannot use, in this case, we cannot calculate the limit directly. But we can simplify this expression. And how to simplify? Just give common denominator. So this is 6n plus 1. Here 2n plus 1. We should multiply. And now limit n tends to infinity. So let's multiply 6n plus 1 times n squared plus 1 minus 2n plus 1 times 3n squared plus 1 over the next one is 2n plus 1 times 6n plus 1. So now let's continue. Here we have, if you open the brackets, 6n cubed plus 6n plus n squared plus 1 minus 6n cubed minus 2n minus 3n squared minus 1 over, if you open the brackets, 12n squared plus 2n plus 6n plus 1. And now let's continue. Here limit n tends to infinity. If you can see here, we have cancelled them, 6n cubed with 6n cubed, and we get the next one. So it is minus 2n squared, and now n's are 6n minus 2n, it is plus 4n, and they are also cancelled. Okay, now we have here 12n squared plus 8n plus 1. Now we can divide by the term of this highest coefficient, so highest power. Here n squared, n squared. This is greatest power of this expression, and we can divide by n squared. So this is now minus 2 divided by n squared. Numerator and denominator, of course. So minus 2 limit n tends to infinity, minus 2 plus 4 over n over, here we have 12, and the plus 8 over n, and plus 1 over n squared. And now, so now they are going to 0. They are going to go to the 0. They are go to the 0. But we have just minus 2 and 12. So the answer is the ratio minus 2 and 12. Minus 2 over 12, or minus 1 over 6. This is the answer of our example. And now, let's consider the next example. So, limit n tends to infinity, cubic root of n squared, sine n squared over n minus 1. So here we have the product of two, we can consider it like separately, two terms, two sequences, n squared and cubic root of n squared and sine n squared. So now, if we put infinity, we don't get the answer here directly, but we can compute it. How? So here again, one more time, let's remember sine it is bounded function. So the greatest value of sine n squared, it is just 1. That's why it goes to 1 when n goes to infinity. So, and now we can change sine n squared with 1, and we have limit n tends to infinity cubic root of n squared over n minus 1. So, which one is greater? I mean, the powers. Here we have first power in the denominator, here we have 2 over third. We can write like in this form also. 2 over third and minus 1. Here first power, yeah? So, the denominator is greater than numerator because the power of denominator is greater than numerator. That's why this denominator goes to infinity faster than our numerator. Hence, we have just form 1 over infinity. This is 0. So the answer of this limit is 0. Because the power of the denominator is greater than the power of numerator. The answer is 0. And now, okay, let's consider the next example. Limit n tends to infinity 2n plus 3 over 2n plus 1 the power of n. So we have some kind of type of the limits. So in this case, this is same with this form, limit n goes to infinity 1 plus 1 over n the power of n. This is number e. We will use this one for the functions also when we calculate the limit of the functions. In this case, we need to provide this fraction to this form 1 plus 1 over n. How to provide it to this form? So let's continue. Limit. Can we write like this? 2n plus 1, we need to divide this polynomial to this polynomial and get the whole part of this fraction. So 2n plus 1 plus 2 over 2n plus 1 and the power of n. So it is limit n tends to infinity. So here we have now 2n plus 1. We can do this one as one fraction and this one is second fraction. So it is 1 plus 2 over 2n plus 1. The power of n. And now we have the form 1 over n. That's why we need to do in this form. So 1 plus 1 over 2n plus 1 over 2. The power of n. Now, we have this form. This is our Sn in this case. But the power is the another one. They should be equal with this power. That's why to use this formula. That's why we need to do, in this case, operation like this, 2n plus 1 over 2, and in the power multiply this 2n plus 1 over 2 and divide by it. So we have here 2n plus 1 over 2 times 2 over 2n plus 1. They gives us 1. But this one now gives us the formula. This formula. And our n, this n we have also. So now this is number e. But we have the limit n tends to infinity. This goes to e. So e exponent, the power of 2n over 2n plus 1. You know, e is the exponent. It is equal to 7, 1, etc. Like the number pi. So here we have now 2n over 2n plus 1, and we can calculate this power also when n tends to infinity. So it is limit, this is like e, the power of limit n tends to infinity, 2n over 2n plus 1. Or it gives us 2n over 2n plus 1 when n tends to infinity, 1. So it is just e the power of 1, or just e. The answer of this limit is 1. Let's consider the next example. For example, limit n tends to infinity so 1 plus 1 over n plus 2, the power of n. So here we have again the formula with e, is number e. Let's continue. So 1 plus 1 over n, the power of n, it is number e. And now let's provide to this form again, limit n tends to infinity. Here we have just 1 plus this one more time, n plus 2. And now in the power we need to multiply this n plus 2 and divide by this one. You have n also, this n. So now they give us number e again, the limit of this sequence. When n tends to infinity, it goes to e, number e. So let's continue. We have the limit n tends to infinity, e the power of n over n plus 2. So now here n. And now let's continue. So limit, or just write limit in the power, e the power of limit n over n plus 2. You can cancel 2 n's, and 1 over n plus 2. When n tends to infinity, it tends to 0. tends to 0 because n tends to infinity. And the answer is e the power of 0 or 1. The answer of our limit is 1. Okay, now let's consider the next example. Now, we have some properties of the limit or some kind of ready limits. Limit n tends to infinity and the power of k over c the power of n. This is equals to 0 when the absolute velocity is greater than 1 and k is natural number. So this is 0. And the next one is limit n tends to infinity logarithm the base of c n over n, it's also 0, whereas c between 0 and 1. And the next one, number 3, it is limit n tends to infinity, so c the power of n over n factorial, it is 0. C, it is real number, any real number, arbitrary real number. Okay, now using these 3 types of the limits of sequences, we will do the next example now. So let's consider this one. Limit n tends to infinity n cubed plus 3n over n plus 3 n plus 1. Okay, now here we can divide by 3 the power of n, numerator and denominator, and then we get the n cubed over 3n plus 1 and n over 3 the power of n plus 3. So they are goes to 0 using the first one, this one and this one. They are go to the 0, and we have just 1 over 3 the answer. Now next examples. So determine if the sequence is decreasing or increasing or not monotonic or bounded above, bounded below, or not bounded. So we need to determine. Firstly, let's write the few terms of this sequence. The first one is 1 over 4, the second one is 1 over 8, 1 over 12, etc. Yeah. So let's consider the nth term and n plus first term. Here 4 we have n plus first term. So this is 4n, this is 4n plus 4. And which one is greater? The nth one is greater. So this is previous one is greater than the next one. That's why this is decreasing sequence, and it is decreasing sequence, and it is bounded above with 1 over 4 because 1 over 4 this is greatest term of this sequence. And if you want to find the lower bound, it is 0. We need to find here limit of this sequence. Next one, 3 the power of minus n. Here again we need to write n from 0 here. 1 over 3 few terms, 1 over 9, 1 over 27, etc. This is again decreasing sequence. And the limit is 0 here. So it is bounded above with number 1 and bounded below with 0. And the last one is n minus 1 to the power of n plus 2, and from 0 till infinity. So if we write the few terms of this sequence, this 0, minus 1, 2, minus 3, 4, the next one is minus 5, 6. So all the ones are negative, the even ones are positive. And in this case, it's not decreasing or increasing sequence, because they are we can consider here it's just 0, minus 1, 2, minus 3. We don't have any increasing or decreasing sequence here. If we consider it separately, for example, even ones or odd ones, we have increasing or decreasing sequence. But in generally, this is not monotonic sequence. And if it is increasing or decreasing sequence, this is monotonic. If it's not increasing or not decreasing, it is not monotonic sequence. And here we don't have upper bound and lower bound in this sequence. So it was last example for today, and the next time we will continue our practices. Thank you for your attention.